As promised, we're going to finish up with self-induction. All right. As you know by now, each loop in a coil interacts with the magnetic field around the current in other. So if we have some coil that a current's going through, of course, you're going to have a magnetic field from the first coil, which will interact with a magnetic field generated from the second, and so on and so forth. So these coils, even though they generate an overall magnetic field, um, like so, um, it turns out you do sort of get some interaction between the coils in the same coil. Um, this process, it actually produces a self-induced voltage that is always in the opposite direction of the applied voltage. So you sort of get a voltage resistance, so to speak, or I guess we could call it a voltage opposition. Voltage opposition. So this is essentially called back EMF. Um, and basically what that means is you just get this uh, strange little extra voltage that opposes the main voltage you're trying to create. Um, and what can happen, let's see if I have it here. Yeah. So if a coil with many loops is powered with a DC source, this is exactly what you might get um, out of this is a back EMF. So if you try to power up this coil with a DC source, it will be accompanied by a strong magnetic field. Yes, we know that. Um, when the battery is disconnected or the circuit is opened, the current falls rapidly to zero. We also know that. And then the magnetic field in the coil undergoes a sudden decrease, right? We know this. We're just talking about one coil now by itself, not two coils. So this whole idea of the changing voltage inside of a coil, it can apply to just one coil and not two. So even in this same coil, the changing magnetic field induces a voltage. So even when we break this circuit, right, we're still going to induce some voltage inside the very coil we're using. Going to induce voltage. Now, this rapid change can actually induce a voltage that can be very large, and that can cause a spark. And that's what's going on here. You'll notice we have a battery connected to this uh, coil of wire. Okay, so we just have a battery. We know that is a DC source because batteries are. Okay. Now we see that this circuit has been broken, where it's an open circuit because the switch has been opened up, and then we still get a spark. And that's actually just from uh, the induced voltage inside this single coil. As we change the magnetic field by opening the circuit, we're going to spark from that induced voltage within the coil itself. So normally electromagnets are connected to a circuit that absorbs excess charge, and that'll actually slow down the current changes. So you might not always see this if you open a circuit, if you have a lot of stuff in the circuit, because all of this stuff is going to add more resistance and it will slow this effect, and then you will probably not get a spark. But if you just have a conductor and a battery, you're likely to see a spark from that back EMF. Now, what's really interesting is we could actually use this idea of self-induction to actually do something called magnetic braking. Okay, so the best way to describe this is to just consider this demo over here. Um, so what happens is you have a section of copper plate that you can like let swing through a magnetic field. Okay, so you can see that there's a magnet right here. and this copper plate's going to swing right between the north and south poles of this magnet. So what happens is as the section of the copper plate enters the magnetic field, then there are free electrons inside the copper that start swirling in the shape of an eddy current, essentially. So it's sort of like water swirling around in like a small stream or creek or river. So the idea is the magnet is going to start moving the electrons, and you'll actually get little eddy currents of these electrons in here. So the eddy currents themselves essentially are little electromagnets, and they actually are repelled by the outside magnet. So this actually slows the copper plate. So these eddy currents and this magnet, they essentially resist each other. Okay. Now that's actually, this resistance is going to slow the copper down. Okay. So uh, this will slow the copper plate. Now, as the copper sheet leaves the other side, okay, so let me change colors. We'll talk about this now. So as the copper plate leaves the other side, well, as it leaves the other side of the magnetic field, these eddy currents swirl in the opposite direction. Okay, so now they are actually attracted to the magnetic field. So when you get over here, you get eddy currents going the other way, and this will be in our copper plate. And then on this side, they don't resist, they are actually attracted. So you have, let me use yet another color. So you have slowing down on one side from resistance, then you have slowing down again on the other side. And that's from just trying to pull the plate back toward the magnet. So on one side you have resistance slowing it down, the other side you have an attractive force slowing it down. And you can see in this GIF here, hopefully it's working for you. As this ball bearing comes through into this magnet, see how it sort of starts slowing down right here in the middle? That's exactly what this copper plate would do. It would just swing and then swing and get really small back and forth, really small oscillations, and then just stop right in the middle. But that's the idea of magnetic braking. Um, so both of these effects, as far as the induction of eddy currents, uh, these involve the conservation of energy, and they actually illustrate Lenz's law, which basically says induced effects oppose the inducing cause. And we saw that. We saw that the inducing cause was the big magnet on the table, and then the induced effect, the eddy currents, they actually opposed the big main magnet. Okay, so those eddy currents. So the eddy currents was responsible for opposing. Magnetic braking is actually commonly used to slow like high-speed trains, trucks, and cars, and even the blades of wind turbines. And the beauty of magnetic braking is there's no like friction, there's no brake pads. So that's fewer parts that need to be replaced. And you're literally slowing down some object simply just by using fundamental physics and not like mechanically engineered parts. Um, so things tend to last a little longer when you use magnetic braking. Okay, let's look at power transmission for a second, because this this entire lecture is going to be shorter and just talking about applications of induction. So let's move on to another application here. So um, almost all of sold is in the form of AC just because you can actually transfer AC over great distances. Um, you can also easily transfer, and then also with large currents in wires, a lot of times those large currents will produce heat, and generally heat is something you don't want because that leads to power loss. So if your power is transmitted over a great distance at high voltage and low currents, it's actually more efficient. So that's something you can get out of this just by stepping up voltage using induction. You can transfer power across the US at super high voltages, but very low current. So power that's generated at like 25,000 volts is often stepped up to like 750,000 volts for transmission and then steps down again in stages. So just this cartoon here sort of demonstrates that. So you have the waterfall from like a dam that's actually going in and to a turbine. Okay, so here's the generator. It's going to spin the generator, spin the armature, which is going to generate a voltage, generate electricity. Then you'll need to step it up. Okay, so we're going to transmit this over power lines at a very high voltage, but a low current. Okay, and then we may need to step that down or step that up again. So we have more voltage transitions here. Um, Again, we'll still have fairly high voltage when we transfer over this long distance. And then right here at the end, we'll step this down one more time to roughly 120 volts or 240 if you have a very nice like washing machine or stove that uses 240 volts instead. Um, so this is the whole process, and it uses a series of like transformers and inverters, things like that, to actually go through all these steps of getting to a high voltage and then stepping it down once it gets to your house. Something else to talk about is just sort of summing this up. Field induction. So the modern view of electromagnetic induction is that electric and magnetic fields are induced, um, and then these in turn will produce voltages that we've been talking about. So the important thing here is the word fields. Uh, Induction occurs obviously when there's whether a conducting wire or a material medium is present or not. So we sort of showed that when you move any sort of electron through a magnetic field. I think there's some videos also posted in this course on Canvas that shows just paths of electrons being changed by magnetic fields. So we don't really need the electrons to travel through anything. We just need them to interact with these fields. Uh, that means in the most general sense, Faraday's law can be expressed as an electric field is induced in any region of space, where a magnetic field is changing with time. Okay, so that means a changing magnetic field. So a changing magnetic field will um, induce an electric field. And then, of course, we have Maxwell's counterpart to Faraday's law, which states that a magnetic field is induced in any region of space where an electric field is changing. So this actually goes both ways. We can change the electric field and generate a magnetic field, or change the magnetic field and generate an electric field. Which means the induced field is essentially proportional to the rate of change of the inducing field. Okay. So what you make is going to be the same frequency or same rate of change as the thing making it. Um, and we'll talk about this later in the next module, I believe, because we're going to move to uh, light and photons. And photons are just a combination of electric and magnetic fields. But induced electric and magnetic fields are actually at right angles to each other. And you can see that in this GIF that's playing over here. Hopefully it's playing for you. Um, these magnetic fields are always at right angle, or these two fields are always at right angles, and they sort of oscillate as such. It turns out that Maxwell actually saw the link between electromagnetic waves and light. Okay, so here's the electromagnetic waves. This is electro plus magnetic waves. So we have an electric field plus the magnetic field. And for short, physicists will call this E&M for electricity and magnetism or electromagnetic dynamics, things like that. So Maxwell saw that E&M was related to optics, so related to light. And if electric charges are set into vibration in the range of frequencies that match those of light, so essentially, if your electric charge vibrates in the visible light spectrum, then actually visible light waves are produced. And that's something we'll talk about later. Um, and Maxwell, essentially, to sum it up, discovered that light is simply electromagnetic waves in the range of frequencies which we can see. So really, light is just oscillating E&M waves, which is very bizarre. And again, we'll hit that later. So that's summed up all of the applications. Didn't use a lot of external sources. If you're interested, though, there is this entry on Tesla if you'd like to read more on him. Otherwise, if you have any questions about magnetic induction, do let me know. And after this, we'll move on to a new topic.